Hello everyone, I'm Nabiha from Team 3. Today I would like to present on carbon emission pinch analysis. So there are two approaches for carbon pinch analysis, which are graphical method and numerical method. For part 1, I will be explain on graphical method for carbon pinch analysis, where we will be introduced to source and demand curve SDC. First of all, for introduction part, I would like to give brief explanation on pinch analysis applied in carbon planning. So, the first developed pinch analysis being used for the optimal design of heat recovery networks for processing plant. However, the pinch analysis is not only limited to design of heat recovery network, as it also has successfully applied and adapted in different areas such as resource minimization, material conservation, energy audits, and few more. It also be a tool for carbon emission reductions and planning, that known as holistic waste to resources. It is a process integration approach for carbon planning that based on the classical pinch analysis technique. Why it is said to be holistic? This is because it allows designers and planners to systematically screen and prioritize which option to minimize fresh carbon as well as carbon emission, either via elimination, reduction, reuse or recycling, outsourcing, and regeneration using the carbon management hierarchy (CMH). I will be explaining on CMH in next few slides, focusing on level 1. At the same time, the application of holistic approach at a refinery site results in maximum potential CO2 reduction up to 95%. In carbon network for industrial parks, the process integration approach for carbon planning are based on the classical pinch analysis technique. The holistic waste to resources was implemented to plan and design a minimum carbon network for industrial park. There are different flue gas sources that commonly released in industrial site. These flue gas also known as stack gas. They may be from the furnace stacks, boiler stacks, drying tower, gas turbines, and also cogeneration plants. It made of different stack gas such as nitrogen, nitrogen oxide, and other gases, as it is depending on fuel use and the extent of the combustion. There are 4 steps to implement carbon emission pinch analysis using graphical method. The first step is carbon sources and carbon demand data extraction, followed by targeting the maximum carbon exchange and setting the holistic minimum carbon target. The last step is designing minimum carbon emission network. In step 1, the carbon source and demand data are extracted. First, we must identify the source, and then the demand being planned and designed. Usually, the demand include processes such as syngas manufacturing from CO2, microalgae cultivation, enhanced oil recovery, methanol production, and also beverage manufacturing. For CO2 source, the data on flue gas flow rate and also the composition of CO2 in flue gas is required. While for CO2 demand, the data on flow rate of gases that can be accepted by the demand process and also data on limiting CO2 composition in the gas are required. However, please bear in mind that not all the available carbon source can be used. Why? This is because some may contain hazardous substance. They may be remotely located anywhere or have smaller CO2 concentration that is not suitable. This slide shows some example of demand process in carbon planning. First, syngas manufacturing from CO2. Second is beverage manufacturing. CO2 is widely used in the food industry for applications such as removing the caffeine from coffee beans and also being used for carbonating drinks. So, carbon dioxide is also used for cooling in the food industry. Next, the demand include process of methanol production. CO2 must be purchased pure, which is more expensive and treated to food grade quality for a beverage plant. So building this plant in the vicinity of CO2 sources provide access to relatively cheaper food grade CO2 because transportation costs are eliminated. For CO2 enhanced oil recovery, significant volumes of carbon dioxide emission can be stored while increasing the domestic oil production. Lastly, CO2 from appropriate point sources can be reused for microalgae cultivation. Come to step 2, which is targeting the maximum carbon exchange. This step involves the construction of source and demand curve (SDC) for CO2 targets. The reason for SDC was developed because to address the unique carbon exchange problem. SDC constructed by plotting the cumulative flow rate of other gases other than CO2 versus cumulative flow rate of CO2. The y-axis will indicate the amount of impurities in flue gas, while x-axis indicates the amount of CO2 available in the flue gas. I wanted to highlight on unique carbon exchange problem. In previous pinch analysis studies of mass, gas and property, the mass flow rate of a main or primary carrier fluid was plotted against the mass load or concentration of the contaminant or minor components in a process stream. This approach is not applicable when dealing with gaseous stream containing CO2 because CO2 may not be the main carrier fluid. For example, a flue gas stream can consist of CO2 and a larger percentage of various other gases such as nitrogen, nitrogen oxide, and others. For CO2 targets, using the conventional plot of my primary gas flow rate versus the mass load of contaminants yields the minimum flue gas emissions target instead of the minimum carbon emission target. So continue on step 2. Source and demand are arranged in ascending concentration order. So how we want to obtain minimum fresh CO2 and emission flow target? After we implement step 1 and step 2, the SDC being constructed. So we will move the whole source curve horizontally at 0 FOG until it touches the demand curve. From there, we will obtain the pinch point. This pinch point is the point where source and demand curve touch each other after being shifted. Step 3 is setting the holistic minimum carbon target. Further reduction in the fresh and emitted carbon targets achieved by exploring process change options given by the carbon management hierarchy priority level. There are 4 levels in CMH. Direct reuse are in level 1, source and demand manipulation in level 2, regeneration reuse for level 3, and lastly level 4 is carbon sequestration. This level is according to its priority. Level 1, which is direct reuse, involves the use of point source of CO2 emission to satisfy various CO2 demands without any treatment. The maximum carbon exchange target represents the total flow rate of all the emission point source that can be directly reused and integrated with various demand process. The direct reuse level involves using the source and demand curve to integrate demands with emission point source to determine the maximum carbon recovery and the minimum carbon emission targets. In holistic carbon planning, direct reuse is recommended as the top priority option of the CMH. Step 4 involves designing a carbon distribution network that achieves holistic minimum carbon emission targets by applying the graphical gas distribution network design technique. However, for part 1 video, I will cover up until targeting only, which is until step 3. Here come two quick examples. As mentioned in step 1, the source is identified while the demands are planned. The data required for both source and demand are as shown in the table. The cumulative value is obtained in step 2, where the value is added by the previous flow rate. For example, the flow rate of source 1 is 36 and flow rate of source 2 is 49. If we add the both value, the result is 89. Same goes to demand side to obtain the cumulative value. So, these two cumulative value later will be used to plot the source and demand curve, SDC. So, what data we will be obtained from the graph? From cumulative value calculated and constructed both source and demand curve, we will shift the whole source curve towards the demand curve until both curves touch each other. The point it touches is the pinch point. From there, we can determine the minimum fresh CO2 target and CO2 emission target. As you can see from the graph, the left-hand side of the pinch point is known as the region below the pinch, and the right-hand side is known as the region above the pinch. The overshoot of the source curve gives the minimum CO2 emission flow rate, while the horizontal gap between the demand and source curve at 0 FOG gives the minimum fresh CO2 flow rate. So this example shows that integrating the emission source with the carbon demand to achieve the maximum carbon exchange can reduce emission. So, I would like to recap and make quick conclusion for part 1. In summary, holistic approach is implemented in industrial carbon planning known as holistic waste to resources. Any potential emission point sources are integrated with planned carbon sinks or carbon demand. In part 1, we already be introduced to source and demand curve as visualization tool or graphical method for unique carbon exchange problem. I think that's all for part 1, but further detail on source extraction example, demand planning and also graph plotting will be continued on video part 2, which will cover study case for petroleum refinery area. So thank you everyone. Hopefully everyone can digest my explanation well. See you again in next video.